Corrosion, the way to define it is to say is a reaction of a metal, and it's going to react with oxygen in the presence of water. Okay, the way they're going to award the marks in that one, they're going to use one there and one there in order to gather the marks. Next one is a calculation. So let's have a quick look at this one. What I like to do with these, and I advise you to do the same, is transfer the information that's written into the equation so we can see what we're trying to do. So I can see here, we calculate the maximum volume of nitrogen. So I'm just going to put some little question marks underneath nitrogen because that's what I need to find. That's produced from 110 grams of this sodium azide. And we're told the relative formula mass is 65. I'm also told that 1 mole of any gas occupies 24 decimeters cubed. Right, let's go for this. So first job, step one is I don't want to work here in grams. I want to convert this to moles. So I'm going to use this triangle here to find the moles. And moles is mass divided by mR. So my first job is moles of NaN3 is going to be the mass divided by the mR. So the mass in this example is 110. The mR we're told is 65. Let me just grab my calculator. So 110 divided by 65 is giving me an answer of 1.69, and that's going to be moles. Okay, next job, number 2, is I'm going to use the ratio. So if you look at what we're trying to do here, we've got to go from here to here. So there's a ratio change. So let's write that out underneath. Step 2 is the ratio. So I have got 2 lots of sodium azide, and it's forming 3 lots of nitrogen. We've just worked out that we have got 1.69 of this. So what I'm trying to do here is get from here to here, and I'm trying to get therefore from there to there. So what I'm going to do in this example is you times by 3 divided by 2. So let's put that on here. So times by 3 over 2 times by 3 over 2. So times that by 3 divided by 2. I'm getting 2.5. 38. So it's a big long number, so I'll leave it there. Okay. Third step. We now know that we have got this many moles of nitrogen, but the question was to work out a volume. So I'm going to use this triangle to work out the volume. To work out volume is moles times 24. So the volume of nitrogen equals moles times 24, which is this 2.538 times by 24. So let's just do that. Times that by 24. And that's given me an answer of 60.9. 60.9. And that would be in decimeters cubed. The answer here wants it in centimeters cubed. So what I'm going to do there is times that by 1,000, and that's given me 60,923 centimeters cubed. So to get from there to there, we just multiply by 1,000 to make that work. Again, marks in that question, it's 4 marks in there, so working out the moles, doing the ratio, working the answer out, and then converting it into centimeters cubed is how they will give you the credit for that particular answer. Okay, the final one is a 6 marker. Let's have a quick look. Again, I like to try and break this into stages. So I'm going to add 2 more stages. So the similarities and the differences are going to be included in here as well. So we're going to first of all talk about pure substances, and what the properties are. Then we're going to talk about the alloys of these two and what their properties are. And then we're going to look at the similarities and differences and try and explain why that happens. Okay, so the pure metals, aluminium, copper. Here are some features, properties that they have. So you can see they are shiny. They're good conductors of heat, good conductors of electricity, sort of standard stuff. Ductile means it can be drawn into wires. We know copper wires, they're pulled out. Malleable means bendy. Copper is unreactive. Aluminium is also unreactive. If you remember, it has a layer of oxide on its surface, which means it doesn't react. And aluminium has a low density. Okay, so again, bullet points I've done here, but you'd be writing this out in sentences. But that's the content we'd be looking for you to have in your answer. Second list, alloys. So alloys, yeah, good conductors of heat as the elements are. Good conductors of electricity. They are strong and probably not as malleable because they are stronger, and that reduces their ability to bend them. Brass is an example of a copper alloy. Brass is sonorous, musical instruments. That's why we hear the sounds that they produce. And brass is also hard wearing. So think about door handles and fixtures and fittings. It's a hard wearing material. Magnesium is an aluminium alloy. It has a low density, but again, higher strength than pure aluminium would have. Okay, so we've kind of gone through stages 1 and 2. It also asks us to do some uses for these. So here are some uses. So the pure metals, aluminium first. So takeaway trays, they come in aluminium trays. Cooking foil, tin foil. Copper is used in water pipes, electrical wiring. And then the alloys, the aluminium alloys, you've got aircraft parts and car bodies. And copper alloys, we have got coins and brass instruments, hard wearing, and again that looks nice and sonorous sounds. Okay, then similarities. So both structurally contain lattices. So you've got cations surrounded by a sea of delocalized electrons. This means they will conduct heat and electricity because those electrons are able to move. And both will have high melting points because the bonding inside them is strong, okay, and requires a lot of energy to break. Differences between them. So I've got here a diagram. I think diagrams are always powerful to include in your response. So here, this is an alloy, and we'd normally have layers for the pure metal, but what happens is when we put an alloy in, the particles are different sizes, and therefore the layers are disrupted, and therefore the layers, it's not as easily slid, and this makes them stronger and less ductile, less malleable, because these changes mean that this layer can no longer slide as easily. Okay, so I've put those bullet points there to explain the picture. I've also said that pure metals have very specific melting points. So they will melt at a certain temperature, whereas alloys will melt over a range of temperatures. And I've also said that alloys, another difference is alloys use requires a greater strength than the pure metals. And that's why we have to make the alloys in this way, because that gives us the extra strength in there. What I will do is a lot of bullet points there. I'm going to count them up, and I'll put a little chart on the bottom here, and you can have a look at how you scored against that when we load that up. Thanks for listening. Hope it all made sense. Hi guys, I said I'd just post a little bit at the end. This is it. So count up your bullet points and then give yourself this many marks depending on how many bullet points you got in your response. Remembering, we've got to fill it full of knowledge, so we're aiming to get ourselves into this kind of category with all the information that we know.